Good morning, sir.
Good evening.
Sorry, sir. Good evening.
Okay. Good evening. I am
Good evening,
Saurabh
sir.
and I welcome you to this session for the NPTEL course, IC engines and gas turbines. Okay. So today is our session 7 and this is introduction to gas turbines. Okay. So our course is IC engines and gas turbines, right? So IC engines means uh, so in IC engines, as the name suggests, that combustion takes place inside the chamber, right? So for example, there are some steam engines, right? So in steam engines, the combustion takes place outside your working fluid. Okay, so there is some chamber. Okay, so this is your chamber, and there in this chamber there is working fluid, that is steam or water, and combustion is taking place outside this this device, right? So this is external combustion engine, right? But in an internal combustion engine, that combustion takes place inside the device, right? So inside, okay, so in external combustion engines, the combustion takes place outside the engine, right? And in internal combustion engines, the combustion takes place inside your engine. Okay, so this is your engine and working fluid is inside this engine and combustion takes place inside this engine. And the combustion products are itself, they themselves are the working fluid, right? The air fuel mixture, and after combustion, the burnt gases. So all these combustion products, they themselves are working fluid. Okay. So for example, in our diesel engine or SI engine or any type of reciprocating engine, the combustion takes place inside your engine. And in gas turbine also, the combustion takes place inside the engine. So gas turbines are also a type of internal combustion engines. Okay. But most of the books and most of the times when we say IC engine, then most of the time we are referring to reciprocating engines. Okay. And gas turbines also being the internal combustion engines, but they are so vast and their mechanism and their working principle is very different as compared to reciprocating engines. So they are discussed separately. Okay, so most of the IC engine books, they don't include this gas turbines, but there are some good books, okay, some old good books, they also uh, include the gas turbines. Okay, so anyways, so gas turbines, as the name suggests, that gas turbines are turbines. So turbines are a type of turbo machine, right? And turbo machine, what are the turbo machines, right? So turbo machines, as the names they suggest, turbo. So turbo means something is rotating, right? So these are rotary machines, right? And IC engines or the reciprocating engines, they are positive displacement machines. Okay. So from this session onwards, we are starting discussion on the gas turbines, and the gas turbines are turbo machines. So the concepts of turbo machinery will be used here. Okay, so concepts of turbo machinery means there are some velocity triangles that you might have studied in your thermodynamics. Okay, so those types of concept of turbo machines will be used here. Okay, so in this session we will be mostly reviewing or will be revisiting the definitions, what are various terms. Okay, so not much numerical problems, only some conceptual and definition based problems. Okay, so let's start. So we have question number 1. Okay, so the correct option is is shown in bold, so we have the correct options. Okay, so first question asks, in a gas turbine used for electricity generation, the primary thermodynamic function of a stator component within the compressor stage is 2. So you know that there are various stages in turbo machines. Okay, so there are some rotors and there are some stators. Okay, And one more thing, that there are two types of turbo machines. One are power producing, right? And other type is power consuming. So power producing devices are those which gives you some work output, and you are providing heat, right? You are you are burning some fuel. Basically, you are providing heat, and that heat is being converted into work. Okay, so those type of machines are power producing devices, and another type of devices are power consuming devices. So you are giving some power input. So power input may be in the form of electricity or maybe form of mechanical work. Okay, so those are power consuming devices, and those type of device can, you know, they can basically compress the air, or they can increase the pressure of a fluid. Okay, so two types of devices are there, right? So but the whole process can take place in various stages. Okay, so those stages are, completed using various sets of rotors and stators. Okay, so here it is saying compressor, right? Compressor stage. So compressor, it is a power consuming device. You give some power input and it compresses the air, right? So in compressor, again, there are two devices, stator and rotor, right? So stator, as the name suggests, that they are stationary, they are not moving, and rotor, they are moving. Okay, so rotor, since they are moving, they impart the kinetic energy to the fluid. Okay, they provide some kinetic energy to the air, and then that air goes into the stator, and stator converts that kinetic energy into pressure. Okay, so it increases the pressure, right? So this is the main function. So rotator is rotating and stator is static. Rotator provides kinetic energy, and stator converts that kinetic energy into pressure energy. It increases the pressure. Okay, so there are a lot of stages, right? So there will be a series of stator, rotor, stator, rotor, stator, rotor, like that. Okay, so there are four options. Option A says that supplies kinetic energy to the working fluid. It is asking about stator. So supplies the kinetic energy to the working fluid, increases the overall energy. So it is not correct. It increases, sorry, it is stationary. So it converts the kinetic energy into pressure energy, right? And it increases the pressure, but it does not supply the kinetic energy. Rotor supplies the kinetic energy, right? Option B says facilitate the transfer of energy from working fluid to the rotor, enabling the rotation. So it is also not correct. Okay, because we are not enabling the rotation. We ourselves are providing the energy to rotate the rotor, right? Option C says convert the kinetic energy of the working fluid into pressure head, increasing the static pressure. So yes, this is the correct option, right? Option D says maintain a constant area passage for the working fluid to ensure impulse based energy is transfer. So this is also not correct, right? So now it should be clear the difference between stator and rotor. Okay. So moving to the next question. Question number 2. It says considering the differences between impulse and reaction turbines. So two types of turbines are there, right? Impulse turbine and reaction turbines are described in the sources. Sources means basically lectures. Okay. A key characteristic that leads to higher efficiency in reaction turbines compared to impulse turbine is the. Okay, so just ignore these lines. A constant area passage between the rotor blade that maximizes the impact force of the fluid. Absence of any pressure change across the rotor blade, relying solely on intake kinetic energy. Option C, converging passage between the rotor blades that allows for the continuous acceleration as well as the pressure drop across the rotor. And option C says greater susceptibility to boundary layer separation within the rotor passages, promoting the better mixing. So it is saying that reaction turbines are having more efficiency. So what is the reason? So in impulse turbines, the passage area remains constant, right? So passage area means area between rotor blades. It remains constant. So this is not correct because it is asking about reaction turbines because they have higher efficiency. So why they have higher efficiency? So constant area, no. Reaction turbines don't have constant, passage area. They have converging passage area between rotor blades. Since the area is converging, so because of continuity, the velocity increases, right? The velocity increases. So there is some acceleration, right? So there is some acceleration. And velocity is increasing, the pressure will be dropped, right? Correct? So option C is the correct option.
Yes, sir.
So I think we have not studied the degree of reaction right now, right? In this week, maybe in week 8 it will be discussed or later. So there's something called degree of reaction. So based on that, we can differentiate between two types of turbines. Okay. Anyways, for the time being, just realize that impulse turbine, the passage area between rotor blades is same, but in reaction turbine, it is converging, and because of this conversion, the velocity increases. So there is some acceleration and there's some pressure drop. Okay. So now question number 3, it is saying that for a gas turbine operating with a twin shaft arrangement, a significant advantage over a single shaft arrangement arises when the application requires option A, maintaining a fixed rotational speed and the load, as in large scale electricity generation with constant demand. Achieving the highest possible overall cycle pressure ratio for the maximum thermodynamic efficiency. Flexibility in operational speed and load, such as in marine propulsion or driving pipeline compressors, or maximizing the complexity and cost of the initial plant construction and maintenance. So option D is of course wrong, right? Because it is asking about advantage and increasing complexity and cost. Of course, that is not an advantage, right? That this is not an advantage. So there are two terms: single shaft and twin shaft and single shaft. So as the name suggests that there are two shafts. Okay. So in single shaft, there is only one shaft and the compressor and turbine and of course there will be combustion chamber. Okay, fuel will be added here. Just a second. Okay, so fuel will be added in this combustion chamber, and that will be burnt, and we will get some energy, and that will be transferred to turbine, and the turbine will rotate the compressor. Okay, and load will be connected with the same shaft. Okay, so this is single shaft arrangement. And in twin shaft arrangement, as the name suggests, that there will be two shafts. Okay, so compressor, it is getting power from turbine. Okay, so of course there is some combustion chamber, and fuel is added here in this combustion chamber. Okay, but there will be another shaft, right? Another shaft, and that will be combined with another low pressure turbine. Okay, so what are these high pressure turbine, low pressure turbine? That will be discussed, I think, in later lectures. Okay, so this is high pressure turbine, and this is low pressure turbine, and there is another shaft. Okay, so this is single shaft arrangement. This is twin shaft. So now you have two shafts, so you have flexibility. So whenever you don't have constant speed and load is also changing, so in that case it is quite helpful, right? Because if you have the single shaft, then it is good when there is constant load or constant speed. For example, you have a power plant, steam or I mean gas power plant. So in the power plant, usually the speed and load, they are constant for a longer time. But for in marine applications, for example, you have a ship. Okay, so in the ship, your speed is not constant, the load is also not constant. So in those type of applications, you need some flexibility in terms of load and speed. Okay, so in those cases, this twin shaft turbines are important. Okay, so this is the advantage of twin shaft arrangement as compared to single shaft, because they can provide uh, provision for variable load and variable speed. Okay, and maintaining a constant rotational speed, this is not correct. So only option C is correct, right? Anyways, question number 4. It says, in a closed cycle gas turbine power plant, the ability to pressurize the working fluid to level above the atmosphere pressure throughout the cycle offers a significant advantage, primarily by. Okay, so it is asking what is the advantage of increasing the pressure more than the atmospheric pressure in case of closed cycle gas turbine. So what are closed cycle and open cycle. So option A says eliminating the need for a compressor. So no need to read further. It is not correct, right? Because since you are increasing the pressure above the atmosphere pressure, then definitely you will need a compressor. Okay, so it is not the correct one. Option B says allowing for the use of external combustion without the risk of turbine blade erosion from the combustion product. So this is also not correct, right? We are discussing, gas turbines, and gas turbines are internal combustion. Option C says increasing the density of working fluid, leading to a reduction in physical size of turbo machinery component. So this is the correct option. You have the closed casing, okay, closed cycle, and you are compressing the fluid. So the density is increasing, but the specific volume is decreasing. So your overall size of the machine will be reduced. Okay, so there will be reduction in the physical size of the turbo machinery components. So this is the correct option. And option C says enabling the direct use of atmospheric pressure as the working fluid, simplifying the system and reducing cost. So this option is not, not the correct option. Okay. So one more question. Question number 5, considering a combined cycle power plant integrating a gas turbine and a steam turbine. The primary reason for utilizing high temperature exhaust gases from the gas turbine in a heat exchanger connected to a steam cycle is two. So it is talking about something called cogeneration that probably we'll study later. Okay, so what happens in a gas turbine? Uh, Exhaust gases which are coming out from the turbine, they are quite, hot. Okay, so they have a significant amount of enthalpy, and instead of throwing that high enthalpy gases directly into the atmosphere, we can utilize that enthalpy to run another turbine. Okay, so we can run another turbine, or we can use the heat of those exhaust gases to heat the water. Okay, you might have studied the preheating in case of uh, steam power plants, right? So instead of wasting that heat of exhaust gases, we can utilize that. Okay, so it is talking about, I think, the same thing, right? Utilizing the high temperature exhaust gases from the gas turbine in heat exchanger connected to steam cycle. Okay, so we can preheat the water, right? So we can utilize this energy of the exhaust gases. So four options again: you reduce the temperature of exhaust gases before releasing them into the atmosphere, minimizing the environmental impact. Well, this is not completely wrong, but this is not the purpose, right? This is not the purpose, right? We want to just utilize the heat of the exhaust gases, right? Directly power the steam turbine by mixing the hot exhaust gases with the steam generated by a separated boiler. So this is not correct. Recover the thermal energy from the gas turbine exhaust to generate high pressure, high temperature steam, thereby increasing the overall plant efficiency. As we have discussed earlier as well, and probably we will discuss in upcoming sessions as well, that the average temperature of heat addition is increased, then efficiency will increase, and the average temperature of heat rejection is decreased, then the efficiency will increase. Okay, to increase the efficiency, basically we are trying to increase the mean temperature of heat addition, and we are trying to reduce the mean temperature of heat rejection. Okay, so in case of a steam power plant, if you are preheating your water, okay, or steam, then you are increasing the mean temperature of heat addition. Okay, so you are increasing the efficiency on the expense of the heat of exhaust gases. Otherwise, this heat of the exhaust gases will be wasted. Simply you will throw those exhaust gases into environment. Now you are utilizing and you are increasing the efficiency of your steam power plant. Okay, so this is the correct option. We are recovering the thermal energy from the exhaust gases, and we are generating high pressure, high temperature steam in our steam power plant, and we are increasing the efficiency, right? So this is the purpose. Okay, option D says about the preheat air to combustion chamber of gas turbine, reducing fuel consumption. This is not correct. This is not correct. The correct option, if you want to make this option correct, then it should be like reverse. Okay, we can use the exhaust gases of this, gas gas turbine to preheat the air. Okay, that could have been correct option, but this is not the option. Option D is not correct. Okay, it is saying providing preheat to combustion chamber. Okay, so but it is asking about heat exchanger between a gas turbine and steam turbine. Okay, so option D is not correct. Okay, so these questions were some review questions just to refresh your memory about these turbines, and now we will start solving these our regular MCQs. Okay, so let's start. Question number 1. It says which of the following is not considered an incompressible flow machine? Again, 4 options: low pressure blowers, centrifugal fan, wind turbine, and steam turbine. So I think you can easily answer this question if you know what are incompressible flow machines. So in compressible machines, there is significant change in density of the working fluid, right? So in compressible flow machines, there is significant change in the density of working fluid because there are significant changes in the pressure or temperature or velocity. Okay, if the velocity is very high, then in that case also the flow can be compressible flow. Okay, so let us write density, temperature, pressure, or velocity. Okay, so those flows are compressible flows, and incompressible flows are those in which this change are not that significant. Okay, so the machines in which this change is significant, those are compressible flow machines. Otherwise, they are incompressible flow machines. So, for example, low pressure blowers. So, as the name suggests, that it is working on low pressure, not very high pressures. So the change in density will not be that significant. Okay, so they can be assumed to be compressible. Centrifugal fan, again, it is fan, so it is incompressible. So this is incompressible. This is also incompressible. Wind turbine, this is incompressible, right? Steam turbine, this is compressible. Right? Moving to question number 2. Which one of the following is an example of extended turbo machine? So we have studied about extended turbo machine. So in extended turbo machine, there is no casing on or shroud. Okay, no casing or shroud. So they are like open. Okay, for example, your windmill. So windmill is not, it's not closed in any casing. Okay, it is just open. So those type of turbo machines which have no casing or shroud, they are called extended turbo machine. So it is asking which of the following is an example of extended turbo machine. Steam turbine, option A, it is not correct, right? Because steam turbines, they have the casing, right? Gas turbine, they also have the casing. If they don't have any casing, then the gas will, that will not be confined. It will be lost, right? Hydrokinetic turbines. So yes, hydrokinetic turbine, they may not have, they may not have the casing, right? For example, your Pelton wheel, right? They don't have the casing. Okay, the water is falling down from a very large height to those blades. Okay, and those blades are not covered. Okay, they are not closed in a casing. And option D says centrifugal compressor. Again, this is not correct because centrifugal compressors, they have the casing, and because of that casing, they are increasing the pressure, right? So option C should be the correct option. So extended turbo machines means they have no casing or shroud. But the hydrokinetic turbines, so they are immersed in water and they are open. Okay, so they are immersed in water and they are open. Okay. So now moving to question number 3. It says select the correct statement regarding the steam turbine power plant. Steam turbine power plant. So it says that working fluid remains in the same phase throughout the operation. Is this correct? This is not correct. Why? Because it is not in the same phase. Initially, it was water, right? Initially, it was water, and inside the boiler, this water becomes the vapor, right? So it changes its phase, right? It changes its phase from liquid to vapor, right? So there are 4 components, right? There are 4 components. First of all, there is boiler, then, sorry, boiler, then turbine, then condenser, then pump, and then boiler. Okay. So inside this boiler and condenser, phase changes, right? Right. So inside condenser, the phase is changed from vapor to liquid, and inside boiler, phase is changed from liquid to vapor. So phase changes. So option A is not correct. Option B says it has higher work ratio than a gas turbine. So this is correct, right? Plant efficiency is highly sensitive to its component efficiency. This is also not correct because steam power plants have high work ratio, which makes the cycle less sensitive to the component efficiency compared to the gas power plant. Okay. And option D says that it operates with a lower pressure ratio than a gas turbine. So this is also not correct because steam power plant usually they operate at very, very high pressure ratio, right? For example, boiler pressures can be like 100 bar, 200 bar, 300 bar, like that. Okay. And condenser pressure that can be very, very low. Okay. That can be lower than your atmospheric pressure, right? So the pressure ratio is quite high, right? It has high work ratio than a gas turbine plant, right? Okay. So moving to the next question. Question number 4. It says multi-spool arrangement in a gas turbine power plant is typically implemented to achieve which of the following objective? To recover heat loss, to decrease heat addition, to enhance turbine work output, or to increase pressure ratio. So we know that when we are working with high pressure ratios, then using a single compressor, it becomes quite difficult, right? So we are using more than one compressors and they are decoupled mechanically. Okay. So they can have different spools. Okay. Different shafts. Okay. So it is asking about the objective. What is the objective of using multi-spool arrangement? To recover heat loss, this is not correct. To decrease the heat addition, this is also not correct. To enhance turbine work output or to increase the pressure ratio. To increase the pressure ratio is the correct option, right? Because using more than one compressor, which are decoupled mechanically, we can achieve higher pressures, right? More than one compressors, which are mechanically not coupled or mechanically decoupled. To achieve high pressure ratios, we need more than one compressor, right? So option D is correct. So now we have question number 5. It says that axial flow machines generally experience drag force lower or higher, that we have to tell, and are well suited for thrust applications compared to radial flow machines. So there are two terms, axial flow machines and radial flow machines. So axial flow machines are those in which flow is along the axis, okay? Or you can say uh, the axial velocity component is dominating, okay? And radial flow machines are those in which the radial velocity component is dominating, okay? So axial flow machines usually experience less drag or more drag, that we have to tell. So we know that in axial flow machines, the area of contact or the frontal area is less, right? So axial flow machines less frontal area, so lesser drag, okay? And since they have less drag, so they are very, very useful when we require, you know, less drag. And when we require less drag in case of, our aviation purposes, right? For example, aircrafts. So in aircrafts, we want to reduce the drag as much as possible, and simultaneously we also want higher thrust, okay? So axial flow machines are useful when uh, when we require when we want to reduce the drag force and we also want the higher thrust, right? So they are useful for high thrust applications, right? Lower drag suitable for higher thrust. So option A should be the correct one. Moving to question number 6. Which of the following is not a power absorbing or power consuming device? Axial compressor. So we know what a compressor do. So compressor basically requires some external power, right? It requires some external power that can be in the form of electricity or that can be in the form of mechanical work. Okay. And this compressor converts this external work into the pressure energy, right? It increases the pressure head. So it is absorbing the external power. So it is a power consuming device or power absorbing device. Option B says a centrifugal fan, and option C says gas turbine, or option D says blower. So fan, it also requires some external power. So again, it is a power absorbing device. Blower, they also require external power. They are also power absorbing device. Gas turbine, they produce the power, right? We are burning some fuel and this turbine is converting that heat of combustion into the useful work. Okay. So gas turbine is a power producing device. So it is not the power absorbing device. Okay. So the compressor, fan, pump, blower, all these devices are power absorbing devices, right? And the turbines are power producing devices. So option C is the correct option. Moving to question number 7. It says, which statement correctly characterizes an extensive property of a thermodynamic system? So first of all, we should understand what is an extensive property. So as the name suggests, that extensive property that can be extended. So what I mean is that if you increase the size of your system or you increase the mass, okay, if you increase the amount of your working fluid, then this extensive property should also increase, right? For example, weight. So weight, this weight will depend on the mass. So less mass will have less weight and more mass will have more weight, right? But temperature, does the temperature depend on the mass? If you increase more mass, will the temperature increase? For example, you have uh, anything, one notebook, and that notebook will have certain temperature, and you have 10 notebooks, then will the temperature increase? It will not, it will not be affected, right? Because temperature has nothing to do with the quantity, right? So temperature is not an extensive property, but the weight, it is an extensive property. Okay. So there are 4 options. Sorry. Okay, so there are 4 options. And is asking what characterizes an extensive property. So to characterize an extensive property, even you what can you do? You have the system, okay, and it will have certain value of that property. Now you just divide this system in 2 parts. So if the value of the property is also become half or it reduces, then it is an extensive property. And if it remains constant, then it is not an extensive property, it is an intensive property. For example, this is a chamber and it has certain amount of gas, right? And this gas has certain temperature T, some pressure P, and it is some volume V and some mass M. So if you divide this chamber into half, then the mass and the volume, they will also become half, but the temperature and pressure will remain constant. Okay. So the temperature and pressure, they are intensive property, right? They are not extensive property, but the volume and mass, they are extensive properties. Okay. So like that, you can differentiate between intensive and extensive. Okay. So option A, it says it is a path function and depends on the mass of the system. Option B says it is a state function and depends on the mass of the system. Option C says it is a path function and it is independent of the mass of the system. And option D says it is a state function and it is independent of the mass of the system. So one thing is clear that these are dependent on the mass of the system. So either option A or option B. Now, whether it is a path function or state function. So it is saying property. So properties are state functions. They are not path functions. For example, this is your PV diagram. Okay, this is a pressure volume diagram. Okay, this is state 1 and state 2. Now you are reaching from state 1 to 2 from this path I, or you can reach from state 1 to state 2 from this path 2. Okay, so when you reach path 2, the pressure or the volume or temperature at this point 2, this that will not depend on the path, whether you take first path or the second path. The value of these properties will remain constant. Okay, so these are point functions or state functions. Okay, so this is a thermodynamic property. Okay, but if you want to try to calculate the work, then work, it is area under curve, right? It is area under curve. So area under the red curve and area under this black curve, that is clearly, it is different, right? It is clearly different. So this difference because of the path, right? So there's some difference because of this path. Okay, so the work is a path dependent function. Similarly, heat is also path dependent function, but the pressure, volume, temperature, these are not dependent on path. They are point functions or the state functions. Okay, so extensive property, they are independent of path. They are state functions. They only depend but they depend on the mass of the system. Okay, for example, volume, mass. Okay, so these are extensive properties, volume or mass. Okay, so these concepts are from thermodynamics. Okay, if I ask entropy whether it's a point function or state function, or path function, entropy. I write delta Q is equal to du plus pdv, then it is valid only for simple compressible system which is reversible. Okay, but if I write TDS, okay, and del Q is equal to TDS again for reversible. But if I combine these two equations, then it becomes TDS is equal to du plus PdV. Then it is valid for reversible as well as irreversible. Okay. So this is very interesting. Why? Because this one was applicable only for reversible. This was also applicable only for reversible. But the third equation, which we are getting by combining these two equations, that is reversible, that is applicable for reversible as well as irreversible. So why it is happening? It is happening because in the third equation, all the terms, if you see, for example, temperature or entropy or this internal energy or pressure or this volume, all of them are point functions. So the equation which are written in terms of point functions or the state functions, they are applicable for reversible processes as well as irreversible processes. Why? Because all these terms are all these terms are state functions and they do not depend on the path. Okay, and the process, whether it is a reversible process or irreversible process, it is a process. Okay, so it is a path. Okay, so whether is a process is reversible or irreversible, that is path dependent. But the equation which is written in terms of state function, that is independent of path, and that is applicable for reversible as well as irreversible. Okay, so these things uh, are fundamentals and it should be clear what are path functions, point functions, path dependent, right? Now coming to question number 8, it says which of the following describes a closed system in thermodynamics? So again, from the thermodynamics, what are open systems, what are closed systems, right? Option A is system where mass and energy can cross its boundaries with the surrounding. Option B says a system that exchanges only energy with the surrounding. Option C says a system that is isolated from its surrounding, neither exchanges energy or nor mass. Option D says a system where only mass can cross its boundaries with the surrounding. So the closed system, so in closed system, no mass transfer, but energy transfer can take place. Okay, energy transfer can take place. But an isolated system, no mass transfer plus no heat transfer or no energy transfer. Okay, and an open system, mass can be transferred, energy can be transferred. In closed system, mass cannot be transferred, but energy can be transferred. And in isolated system, neither mass nor energy can be transferred. Okay, so it is asking about open system, sorry, closed system. So it is a system where energy can transfer, but mass cannot transfer. Option A, where mass and energy can cross its boundaries with the surroundings. This is not correct. Which exchanges only energy with the surrounding. This is correct. Option C, that is isolated from surrounding. This is also not correct. A system where only mass can cross its boundaries. This is also not correct. So only option B is correct. Right? Now moving to question number 9. It says in comparison to positive displacement machines we have already discussed, right? So positive displacement machines are basically reciprocating machines. Positive displacement means reciprocating. So in comparison to reciprocating machines, the turbo machines operates at high speed and have lower or higher volumetric efficiency. So this is also discussed in the lecture, right? Advantages of turbo machine or the rotating machines. So they operate at high RPM, right? They operate at higher speeds, and the volumetric efficiency is also high. But the pressure ratios are higher in reciprocating machines. Usually, reciprocating machines, they can have higher compression ratios, okay, or the pressure ratios. But anyways, in this question, it is asking about volumetric efficiency and speed. So they operate at high RPM and they have high volumetric efficiency. Okay. And question number 10, it says, what type of process occurs in combustion chamber of gas turbine cycle? So we know in gas turbine cycle, there is combustion chamber. So from combustion chamber, we get gas at high pressure and temperature, and that gas goes through turbine, and from turbine we get some work output, right? So in combustion chamber, we are basically adding some fuel, right? We are adding some fuel, and that fuel is burning, combustion is taking place. So it is asking which type of process is that combustion process is which type of process, whether it is isentropic process or isobaric heating or isentropic expansion or isentropic cooling. So combustion chamber, this has constant volume. Okay, it has constant volume. So there will be no change in volume. So it is neither compression nor expansion. Okay. And now we have two options. It is not compression nor expansion. So whether it is heating, isobaric heating or isobaric cooling, this you can blindly tell. Okay. Definitely we are not cooling in a combustion chamber. Okay. We are heating. And this heat addition, this combustion process takes place at constant pressure. So that's why it is isobaric. And since it is combustion, it is heating process, not the cooling process. And volume is constant. So there is no question of compression or expansion. Okay. So now if I ask that combustion chamber, it is a power producing device or power consuming device. So it is neither power, it is neither, see, the work done inside this chamber is zero. Okay. So it is neither power consuming nor power producing. Okay. It is just heat addition process and power is produced in turbine. Okay. W is 0 since dV is 0, dP is 0. We have one more question, question number 11. Match the following. Path functions. We have two columns. First column, there is path function. Isobaric process relates to extensive property or intensive property. In second column, we have temperature, pressure, enthalpy, or heat. So we have discussed what are path functions. So path functions are those which depend on the path. So let us see all these options. Does the temperature depend on path? It does not depend on the path. It is a point function. Pressure, it does not depend on the path. It is a state function. Enthalpy, it is also a state function. Again, it does not depend on the path. Heat, it does depend on the path, right? Heat and work, it does depend on the path. Okay. So option, so point 1, it should be matched with 4. isobaric process relates to constant pressure, right? So isobaric process relates to pressure. It is a constant pressure process. So option 2 should be matched with pressure. Option 3, extensive property. So temperature, does it depend on the size of the system? It does not. Pressure, does it depend on the size of the system? It does not. Enthalpy, yes, it does depend on the size of system. Okay, so it is an extensive property, but instead of enthalpy, if it would have been a specific enthalpy, then the specific enthalpy is enthalpy per unit mass, right? So enthalpy per unit mass, it does not depend on the size. Okay, so a specific enthalpy, it is not extensive property, but enthalpy, it is a extensive property. Okay, so option extensive property is enthalpy, right? And intensive property, temperature, pressure, these are intensive properties. So 4 will be joined with 1 as well as 2. Okay, and heat, this is not property. Okay, right? So 1 should be joined with 4, right? Because heat, it is path function. Option 2 should be joined with pressure, because isobaric is constant pressure process. And extensive property, enthalpy, right, depends on the size of system. But intensive property, temperature, pressure, specific enthalpy, though it is not given in the question, I'm just writing it from my side. Okay, it does not depend on the size of system. Okay, so I hope this is clear. If there is any doubt, then you can please ask. Okay, so this was last question. So it was just an introduction to turbo machinery, so we did not had much to discuss. Okay, we have not discussed any mathematical relations, or we have not done any derivation related things. So only definition based discussion we had in this lecture. Maybe in the next lecture we can try to solve some numericals, right? I think in upcoming lectures there should be some derivation or formulas, right? But again, these definitions should be clear, right? At least what are power consuming device, power producing device, why we are using stator, why we are using rotor. Okay, this thermodynamic concept, basic review of the thermodynamic concept, you should try to revise all these concepts, and in the next session we will solve some numericals, right? So for the time being, we will stop here and we will meet in the next session.
Okay, sir. Thank you, sir.
Okay, so thank you for joining. Okay,
Thank you, sir.
thank you. Thank you. Good night.
Good night, sir.